So if we're going to look at quantum theory, um, basically we want to consider waves versus particles. We looked at light and we saw how, okay, I mean, at last we left it, right? There was sort of this debate, Huygens and Newton, um, late 1600s, fast forward to like 1802, 1803, Young's double slit experiment, everybody, okay, it's a wave. But it's so we can separate the two out. We can say, okay, we can look at things that are waves, right? If we look at light and we got a double slit experiment, we expect something like this. This is how I might draw the intensity on or represent the intensity on the screen if asked to do something like that on a test, just coincidentally. Right? Because you're just basically saying, well, and the, most importantly, at these points, like here and here and here, right? Like there's zero light gets there, and that's just because of interference, right? We say, well, if you have a wave coming from here, this one would be, well, I guess a trough right now or whatever, or just coming out of it, and this wave here, right? Um, well, the way I drew it was kind of at the same point, so I guess I need to do that again. Right? It would be just about to be a trough. The other one would be just about to be a crest, and so they cancel each other out, right? They're off by a half wavelength or 1.5 wavelengths or whatever, right? And so we get this dark spot, and when you look at an actual screen, it's consistently dark. And then we have this sense of everyday objects, right? Where say something like tennis balls or golf balls or whatever you want, right? You throw them at a screen, and you want to look at the intensity of that, and you sort of expect to see what we expected to see with waves, right? With light, you expect to see kind of if you're looking at the intensity from the first slit, and then the intensity of the second slit, and then sort of this, superposition, if you will. Seems like what you might expect, I imagine. And so you say, well, let's do this experiment then with something else. Let's do this experiment with electrons. And what do we see? Well, we see this. We see the wave thing. And here's a photo of that, right? Here's basically what you might see on a screen. And if you have a screen that actually, detects electrons or lights up, you see interference patterns just like you do with light. And that might seem a bit peculiar, right? They're particles. They're things. So that might seem a bit odd, and to understand that, we kind of got to go back a little over 100 years. So there was a couple issues at the time. Now they knew things like this, but they didn't really quite understand it. One of the biggest things to understand is this, and I didn't write it. Well, this was like Wien's law down below, and so and Rayleigh Jeans. So what they had done is they had sort of put together the equations from thermodynamics and all this, and these are pretty sophisticated, complex equations. So I didn't want to put anything here, but they had kind of figured out. Well, here's what and Wien, this guy here, I didn't get a picture of him, but well, here's what it should look like, right? Here's what the spectrum of light should be depending on the temperature. So they'd figured out that, look, it's the electromagnetic radiation that objects emit depends on temperature. So they knew that. And they'd sort of figured out, really from first principles, really from saying, well, here's the energy, temperature is just the average kinetic energy of these particles, and if they are vibrating or have this much energy, here's what, essentially the spectrum you should see. And this was really known as the ultraviolet catastrophe, because when they looked at those predictions, it predicted this. This was the predicted. right? This was the predicted, and this is not what you see, right? As things get hotter, we don't see the wavelength that they're emitting approach infinite, right? We don't have at this, and you're seeing at the bottom here. Here's the different wavelengths, and the height of the graph, right? This side on the other side really represents intensity, right? So this is saying if you have something that's, let's say, like 500 degrees, like the surface of the sun, this thing would predict that, and that on this level you'd have like infinite amounts, right? It would approach infinity. You'd have so many of these wavelengths of light that it should be just killing us. But that's not what we actually see. What we see looks more like the one that's actually here. So they knew this was the actual one, right? They knew if you were looking at the electromagnetic radiation coming from the sun, it does seem to peak around the wavelength of visible light. Probably no coincidence that that's what our eyes are sensitive to, given that. And so what Planck did, right? He basically worked backwards. He said, well, what kind of mathematical model do I have that fits that? And then what would be the interpretations of that would make this work? And so he figured out that, this works if you say, light are essentially quantized, right? But really, it was a little more subtle than that. He really just said, like, light could only be emitted at certain frequencies. That is essentially what came out of this. And if you had asked physicists at that time, probably they would have said, or possibly they would have said that, okay, like, we're not sure exactly why this is. There were a few other, issues at the time, but they would have said, well, yeah, that's just, maybe there's some reason for that or whatnot, but it's probably not a really big deal. It just turns out that, at least mathematically, the way to predict this is to consider only, that light could only be emitted in certain frequencies, and maybe there's some reason for that, something to do with the particles themselves or the atoms. We don't know. We can still use this though for the maximum wavelength. So you can still, like Wien's law, you can still do, like, the simplified version of this is what you're seeing right here. So if you just wanted to predict the max wavelength, that turns out to be pretty straightforward. And that's, like, in other words, you wanted to figure out if you had something that was 500 degrees Celsius, like the surface of the sun, what would be the max wavelength? And that would be kind of right in here. Note also, if you're looking at something like the sun, it's more toward the green side, but our eyes aren't very good at really detecting that, so it just sort of looks kind of bright light, or like bright white / like yellowish. But interesting that it actually peaks at around the green on the visible light spectrum. Anyway, you can use that pretty much just for something where you just want the peak. It doesn't mean that it's not emitting all these other wavelengths of light, just that's where the max one would be. That's sort of where the peak is. And so you could use that for something like, if you wanted to know this example here, temperature for a peak wavelength of 700 nanometers, so that's red light. If you wanted that to be the peak, you could use that equation and just substitute in 700 nanometers for lambda max, and then solve for t, which means multiply both sides by t, divide both sides by 7 times 10 to the negative 7, and you get a temperature over here, a little over 4. Now, no, this is in Kelvin, so Kelvin starts at 0, like 0 energy. So if you want Celsius, you just add 273 to that, basically. So it's a little bit higher, but when you're at 4,000, I don't think it's a very big deal. Okay, moving on. This was also something that was kind of known, not really well understood, but it sort of follows from a little bit of what we did when we looked at electricity. So this photoelectric effect, if you will, so it was known that different metals require different amounts of energy to get a current to flow. That should kind of make sense just in terms of the properties of different metals, because of their valence electrons and how well they share them or whatnot, right? It's gonna take a different amount of energy to eject an electron from the surface of that metal. So this is known as the work function here, and this is just the minimum energy to remove an electron from the material. So what you see here in terms of this W, that represents that amount of energy. And this is listed here. I just took it from the textbook. You can just see for some different metals what that work function is. And if you want to look at that in electron volts, since 10 to the negative 19 joules is a pretty small number, you could use those units instead. That sort of gives you a sense. And if you look at the different metals, it gives you a little bit of a relative sense of them. So they knew that. They knew when light hits the surface. They also knew this. This is kind of a key, kind of cool thing, right? When light hits the surface of a metal, a current can be generated, which basically just means electrons are ejected. We often pretend it's positive charges, for conventional current, but we know it's actually electrons. Now, here's the really strange part. This is what wasn't understood. Right, that's this part right here. Below a threshold frequency, no electrons are ejected. So, in other words, it was known that if you have a metal, right, like maybe you've got some iron here, right, a little brick of iron, and it's like, well, we know it takes a certain amount of energy to eject an electron, right, in this case 4.67 electron volts, but it wasn't known why, and if you shine light on it, a current will start to flow. So like, okay, light carries energy with it. We know that, we kind of feel that, but it wasn't known why, if you had a low frequency of light or long wavelength, whatever you want to think, nothing happens. You don't get anything. Doesn't matter how intense the light is. It doesn't matter, right, how much of it you shine on this surface. Nothing happens. No electrons are ejected. Once you get to a certain frequency, then electrons start flowing. They start being ejected. And that really wasn't understood, because it was like, well, if these have energy in them, or if light has energy, why is it that this doesn't work? And among other things that Einstein explained in his groundbreaking paper on the photoelectric effect, it was basically, well, this happens because you have to take what Planck did and take that very seriously. And so it was the same conclusion, but a very different interpretation. He really said that no, it really is the fact that light can only be emitted at certain frequencies. It's not that surfaces of materials can only give off these frequencies, but theoretically light could take on any frequency. He said, no, light actually can only take on certain frequencies. It is, and we say photons, he called them quanta at the time, so that's why I sort of put that there in parentheses for you. And that was in, like I said, 1905. He wrote the relativity, or a couple of papers he wrote on relativity were the same year. And this one, which is actually the one he won the Nobel Prize for, although that was in the 20s, and he was already a pretty big deal, so be like Jeff Bezos winning the lottery or something. Like, great, appreciate it. So anyway, that really has some, different results if you look at it that way, and you say, look, the energy of any photon has to be some multiple of this most fundamental number here, right? Which they figured out to be Planck's constant, because he had actually figured this out mathematically. Just, they said, didn't really take it this far in terms of the interpretation. And so Einstein said, yeah, you cannot have photons that are not whole number multiples of this constant, right? And then that sort of makes, well, this is just a graph here showing what happens, right? When you're below the threshold frequency, when light particles, i.e. photons, don't have enough energy, nothing happens. And the best kind of analogy for this I've ever heard is if you kind of imagine, like, you can see this metal here, and here's an electron trying to get it, being ejected, right? And this is like what solar panels and all that are based on, right? Light from the sun hits the metal or material, electrons, which gives you a current, starts flowing. Really, he said, well, you kind of look at it like, imagine the electrons and all their, orbitals and their atoms or whatever, which are kind of usually shared in metals. Imagine that's like you, right? So there's like a bunch of people in here, right? I don't want to do too many, but and you're the electrons, you're stuck in this metal, you want to get out, right? And I say, okay, nobody has any money, but if you want out of here, right? If you want out, this is like a big room you're all stuck in. And I say, if you want out, it costs $6. Right? That's all you gotta do. You gotta pay me $6 and I'll let you go. Well, if I start throwing like pennies or nickels, right? Doesn't matter how many I throw, you're not gonna save up 600 of them to get out of here, right? It's just not gonna happen. But if I start throwing, loonies or toonies down, some people are going to start having enough energy and they're going to collect a couple of them, and then they're going to take off and pay me the price of admission, have a little extra money left over. That's enough for your kinetic energy to run out of the place too. So that's essentially what's happening is you've got photons that don't have enough energy hitting the surface, right? That's not enough energy to actually get the electrons out of their orbits and on a conducting wire or whatever it is you want, right? They're kind of stuck there. But once you get above that, once you give them enough energy that they can actually, escape, if you will, or get out of there, then you start to get a current. And so, as I said, this was kind of a pretty cool interpretation that nobody really took seriously, and was actually the kind of the foundation, if you will, for quantum mechanics and everything that came after it. You can also look at, since we look at the energy of a photon, you could also look at the momentum, and you can see the equation is pretty similar. It's just the energy divided by c, and you can use the relationship here that v, or in this case c, equals f lambda, if you want to go between one of these equations to the other. If you want to go from momentum to energy or whatever, you can just take this and rearrange it and plunk it in up there. No pun intended. So let's take a little peek at this, right? What is the longest wavelength of light that can eject an electron from platinum? So we basically want to figure out this threshold frequency. So for that, we want to know, well, what's the work function? Right, that's going to give me the energy required of a photon. And if you go up here, you can see for platinum, the energy here was just because I think most of the stuff we have is in SI units, I'll just use that. So this says, just looking up on a table, 9.04 times 10 to the negative 19 joules. So that's the energy that a photon needs to have, which means that's 9.04 to the negative 19. And then we know that E equals HF. And this is asking, sorry, this is asking for HF. That's the equation we have up here if you were just looking at it like this. And I also wrote down this here, right? V equals F lambda. We already know that. So for light, right? And then what you can do here is you can divide both sides by lambda, and that means F equals C over lambda, and so then you can replace that. And if I rearrange this, that is multiply both sides by lambda, divide both sides by E, I get lambda equals hc over E. And h, Planck's constant, because I haven't seen it in a while, 6.63, negative 34. And the speed of light we know pretty well. And then there's just the energy that this photon needs to have, which is 9.04 times by 10 to the negative 19. And that means that lambda is 2.2 times 10 to the negative 7. A little less than the human eye could detect. We'd be in the infrared range here if you were looking at something like this. So that would be enough to get a photon, or to get an electron to be ejected from platinum, right? It would, when the photon hits it, if it's absorbed, the energy of that photon would become part of the kinetic energy of the electron. Forgetting what I'm even talking about. All right, another kind of similar example. Suppose an atomic nucleus at rest emits a gamma ray with an energy of 2 MeV. Determine the wavelength and momentum of the photon. So probably at this point you could give one of these a try. Take a few minutes, try this. Take it up. All right, just to remind me, we have an atomic nucleus at rest emits a gamma ray, so we're even told that, so we expect the energy to be really high, as energetic as they get. Determine the wavelength and momentum of the photon. So we know that the E, as last time, E equals HF, and we know that C equals F lambda, which we can rearrange so that we have F equals. And then we can write this as E equals HC over lambda. But we also have this little issue here, right? We're told 2 MeV, which I think is a little bit different from the units that we have if you look at H and everything else that we have. So remember that, so in this case I would say 2 MeV, right, times by 1.602 times 10 to the negative 13 joules per I feel bad. The old version of Apple or iOS, they would straighten the lines, and I got sort of used to that, as if it was some quality I actually had. So maybe they did it just to mess with me. So anyway, yeah, so this way I can make sure, yeah, these units actually cancel. Sorry, that didn't come in very well. Right, and so then that just leaves with 2 times that number for MeV, which equals 3.204 times 10 to the negative 13 joules is the amount of energy that this thing has. Taking this same equation here, that means lambda just equals HC over E. Plugging in the numbers, 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by this energy, which we just found was 3.204 times 10 to the minus 13. And if you put those numbers in, I get lambda equals 6.2. 6.208 times 10 to the negative 13 meters. So very, 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 very small wavelength, which means very, very high frequency, which means very, very high energy, which should be sort of evident from the 2 MeV, which for a photon is extremely energetic. That's not the kind of photons you want to encounter as a human being. And then for part B, we want to determine the momentum. And we know that the momentum is E over C. But that also equals H over lambda. And since I just calculated lambda, that means 6.63 times 10 to the negative 34 divided by 6.208. And I did it this way just because that number is already still in my calculator, which gives me 1.068 times by 10 to the negative 21 kilogram meters per second, which again seems like a really, really small number, but do remember we're talking about a photon. We're talking about a massless particle, which has all of that momentum, right? Which is on the lines of what you'd expect with an electron or something, right? So impressive, really, I think. One last thing to look at going for, and this has to do more with that momentum, because that might seem a bit odd too. Just the idea, right? That, wait, this thing has momentum. Nobody's said anything yet, but it seems like the kind of thing you might say, wait a minute, isn't momentum mass times velocity? And this photon doesn't have mass. So, and so that even goes to the fact that you really have to redefine your concept of momentum, right? That it's not just things with mass that can have momentum, right? Momentum is essentially your ability to apply a force, if you will, right? Which means to push or pull something in some direction if you make contact with it, right? And photons can do that. So they got momentum. One neat experiment that really showed this too is the Compton effect, or Compton scattering. This is getting us all the way to 1923 now. I showed that electrons can be ejected from atoms and can gain momentum. So they basically showed that this is a conservation of momentum situation. If you have an incoming photon, and you can see here, this is sort of represented by like violet light. This is an energetic photon. It collides in an elastic collision with an electron. And what he found was that you get this recoiled electron, if you will, that it goes off at a certain angle, which you can calculate. You probably all remember doing conservation of momentum. Now, these are relativistic calculations, so slightly different and more complex, but essentially the same thing, right? Conservation of momentum. The electron, with its mass, if you will, goes off in this direction, and the scattered photon goes off in a different direction, and it has less momentum than it had before the collision, right? So it's actually, well, I've already said it, a conservation of momentum problem. All right, I have one example here, or just sort of one thing to think about. Explain how Compton scattering is similar to and different from the photoelectric effect. As we saw it anyway, we had electrons in both, right? So both involve photons hitting electrons. Where they're slightly different here, though, is with Compton scattering, right? This is an elastic collision, right? The photon essentially just collides with the electron, right? The electron recoils in some direction and the photon goes in a different direction, right? I feel like I'm losing my ability to word these things a little bit or say it at this point, but that would be essentially what I would say, right? That in Compton scattering, the photon only, like, it's a collision, right? It collides and it leaves with less momentum, although less energy too. I know I said that. Whereas the photoelectric effect, the photon's actually absorbed, and the ejected electron has all that energy as extra kinetic energy, if you will. So, in both cases, there are differences in terms of energy, if you wanted to look at that, but the photon isn't fully absorbed in the photoelectric effect. I would say that would be a pretty good answer too. If someone if you mentioned that, yeah, like in Compton scattering, you do have a photon and an electron after, whereas in photoelectric, yeah, you've really only just got an electron after, right? There is no more photon.